Hi, I'm Manit Mehra. Along with my partner Zoltan, I'm going to be presenting our Advanced Big Data final project, which was on facial recognition and emotion detection using convolutional neural networks on a set of large scale image data sets. So, without wasting further time, let me get started with what it is we're doing and why it is we're doing this. We're going to be focused on, as I mentioned, two particular topics. One is the area of facial recognition. Second related area is the area of emotion detection. Now, why is it that we're going ahead with this particular topic is, if you consider in the current scenario, we have applications which are as varied as applications in health, security, just games, augmented reality, targeted marketing, e-learning, etc., where these particular things are being used. For example, facial recognition is something that you see really picking up as a means of identifying, as a means of personalizing your devices. Your phones, now you have apps to do this for you, actually do have the capability to work with face locks as well, apart from having the conventional pattern recognition that we've already had. With the onset of things such as Google Glass now, the sci-fi reality of looking at the person, being able to identify who that person is, getting a list of details regarding that person, things such as that are now slowly becoming a reality as well. We talk also about the important aspect of emotion detection. Now, emotion detection is pretty useful not just for recognizing whether you're happy or sad and so on, for fun activities or just as a novelty factor. It also finds a lot of application in areas as diverse as e-learning, or in applications which may not be relevant to this, but to something like law and order, where you could consider doing emotion detection for large crowds. Now, what do I mean by that? Let's say you're at a political rally and you want to prevent any untoward incidents from happening before they happen. The best way to do so would perhaps to be to gauge the mood of the audience or the emotion of the audience. This particular technique is one such way of doing that and potentially taking preventive action to do so. A last important area I'll just talk about with regards to facial recognition and emotion detection, and it's a sort of an overlap, is in the area of medical research. Now, consider, for example, this particular image on the bottom right. You have certain key face points. You have certain key points on your face. I apologize. You have certain key points on your face. These facial key points can help determine emotion. They can also help determine things such as the early onset of paralysis. These can be used in detecting these problems before they actually are occurring. And of course, this is a very nascent field. This is something that's really picking up, but this is something that could potentially be very, very useful. The last and perhaps the most fun application or fun area would be in the area of just simple imaging systems. Consider here, for example, Obama having a blast taking a selfie. We are seeing something like this being deployed now more majorly in applications such as Snapchat, something that we do on a regular basis, where you can actually have your face being identified. You can swap faces. You can add effects. You can add stuff to your face, and so on and so forth. Or something like what Facebook is currently doing, where it is able to identify who you are and kind of auto tag you in their images. So these are very diverse areas. These are very varied areas, and in all these different areas, facial recognition, emotion detection can play an important role. So that's where this project has its relevance. The other thing that we could talk about would be perhaps some kind of targeted marketing. So when you're working with focus groups, when you're working with a particular brand that you're trying to target towards a particular audience, trying to gauge the reaction of the audience to that particular brand. So for example, in the US, you have the big Super Bowl commercials, the iconic Super Bowl commercials. These are a very major source of identifying and gauging the reception to a particular to a particular brand. So the ads which are shown in the commercial, or more correctly at the halftime show of the Super Bowl, are major metrics for gauging the mood of a number of products. Let's look at our data set. So for the facial recognition part, we decided to go with a slightly fun task. We decided to go with a fun little celebrity face match. For the purpose of this, the data set that we're using is this data set known as the celebrity face scrub data set, which is openly available. It consists of about 100,000 images of 530 different actors and actresses. This data set in total combines to around 800 MB of data. The challenge with this data set is each of the images are of varying image sizes, considering that they're from different sources. They've been picked up from different magazines, different websites, different entertainment portals, and so on. So the task initially was to kind of just clean out all the faces from the images, and then the next part would be kind of pre-processing the images to a standard set, or more correctly to a standard image size. What we've gone ahead and done is, for all these images, we are resizing all the images, or more correctly all the images of the faces, to a 100 cross 100 size, and more correctly a 100 cross 100 grayscale image size, and that's where we proceed with our subsequent image processing. The other data set that we're using is the Kaggle emotional data, the Kaggle emotion detection data set. This is a data set which is kind of provided by Kaggle. It's a set of CSV files with images which are standard 48 cross 48 images, again grayscale images. Each of these images can be classified into one of 7 emotions. Of these emotions, you will see things such as shock, or more correctly surprise. You will see happiness, sadness, neutrality. You will see disgust, and a couple of more. This is a much smaller data set, therefore in terms of the pre-processing side of things, this was a little bit lighter. Note however the fact that the algorithm that we're using in both of these particular data sets would work with currently the grayscale versions of the images and not the colored version of the images. So let's begin the first one, the high level algorithm, the high level concept. Let's consider first what we're doing for the celebrity matchup. We take an image from the user. This particular image is pre-processed, resized to a 100 cross 100 image, and then we kind of pass it through our convolutional neural network. What you see in this particular image is Zoltan's face first in color. Zoltan's face being pre-processed and resized to a 100 cross 100 grayscale image over here, and being fed to the convolutional neural network. Over here we see Zoltan closely resembles Paul Bettany, I hope I got the name right, who played Vision in the Avengers movies. Going on to the next part of our task, we had this particular task, which was the task of emotion detection. You see me making faces, you see emotions being predicted. This algorithm would be similar over here. Here again, you could take an image of varying sizes, you kind of rescale it, you kind of resize it. In this case, for the emotion detection part, we're resizing it to a 48 cross 48 size image, and we're trying to predict the different emotions. So you see images such as emotions such as disgust, neutrality, you see sadness, you see happiness. I had a blast taking all these photos, making faces at the camera, all for the sake of science. So now let's have a look at it in a little more detail. What exactly is our algorithm? So I said that I'm going to be using a convolutional neural network in my initial celebrity face scrub data set. I will be using a convolutional neural network on my emotion detection data set. So what is a convolutional neural network? First of all, it's a network which consists of essentially 3 layers that you can think of. You typically have a layer which is called the convolutional layer, which basically transforms the images into lower level components, components such as the one you see over here. I will just come to this in a little bit. You have 2 more layers known as the pooling layer and the activation layers. I will not be getting into the details of it very extensively, but again, you can think of the pooling layer as being a sort of averaging layer, kind of downsampling the image to a smaller, more usable level. You typically work with, again, pooling sizes of certain kernels length. Over here I have a 48 cross 48 image. I am using in one of my later stages a pooling size of 2 cross 2, which essentially means every 4 pixels are being given one particular value, rather than me having 48 cross 48 pixels, each of a different value. And finally, you have an activation layer, which kind of again is used to kind of define what the behavior of that particular value will be, or more correctly, how I could map the value of the pixel to an associated value or an associated probability that I could use. Now this is what you will see in these initial layers. These are essentially kind of reducing the image size to a more manageable level, till eventually we come to what are called the fully connected layers. These fully connected layers, as the name suggests, consist of neurons, each of which is connected to each other in the next layer. And these fully connected neurons again will undergo a certain kind of image reduction, a certain kind of image processing, till we finally get an output. Now what's interesting to note is, if I feed in an image such as this, if I pass it through, let's say, the first convolutional neural layer, what I will get is basically features being highlighted by the first convolutional layer. So if I take a convolutional kernel, I kind of I calculate the weights using the forward and back propagation algorithm on the neural net. It gives me a particular convolutional kernel on whom, when I kind of perform this convolutional operation, I see these different kinds of images being generated. So to put it in absolutely simple words, I give an image such as this, I pass it through my CNN. Each of the CNNs gives me a certain kind of feature set. This is the very first layer, therefore it is still human interpretable. In subsequent layers it may become less human interpretable. So again, to make sense of this, what you may notice is, for example, things such as the shape of my head being highlighted in some cases, facial hair being highlighted in some cases. You will see again the contours on my face being highlighted in some cases, and so on. So that's essentially the task of the convolutional network. So to kind of put this in terms of numbers, to kind of throw in the big in our big data, let's talk a little bit about what we're doing. We've got first the face scrub data set. This consisted of a number of different layers. The numbers are on your screen. So I began with a 100 cross 100 image, which is why I had one neuron per pixel. Note that I'm working with a grayscale image, which means I have just one channel. In an RGB image, you would typically have 3 channels, one each for the R, one each for the R, G, and the B channels. Because I'm working with a grayscale image, which is also a single channel, you note that the depth of this neuron field is just a 1. What I'm doing subsequently is I've got my convolutional layers which come in. These convolutional layers convert my images, or they further reduce my images. Each of these images would perhaps be reduced to a depth field of 32 with a 92 cross 92 size that will be visible. This convolutional layer in turn passes on to a pooling layer, which performs further a subsequent reduction on the image size. Like I told you, it's essentially a downsampling mechanism that is performed. In the case of the face scrub data, we kind of performed 2 such layers, a convolutional and pooling layer twice over, and finally we concluded with a fully connected layer and an output layer. The interesting things to note in this, again, a lot of data being given, is we had about 105 MB worth of weight, of just weights. So this would mean that each neuron being associated with a particular weightage, that just the set of these weights came up to about 105 megabytes. We achieved a test accuracy of in the range of 32 to 48%, depending on the values of our convolutional, or more correctly, the sizes of the convolution kernels we used, the sizes of the pooling layers we used, the time we ran our algorithm for, and so on. Our best accuracy was achieved at a training time of around 48 hours. In fact, just a little over 48 hours, and we achieved an accuracy of about 48%. Just to give you a little bit of perspective, if we did not go ahead with this approach, if I had just a random guessing approach, I would have a 1 by 530. That's about something to the order of 0.02% order of successfully identifying or guessing the image. So that's the random probability guessing. We've improved that to 50%. So we've gone significantly higher from a 0.2% to about almost 50%, which is a significant improvement in our overall performance. In the setup of the emotional data set, without again repeating details, we have a similar convolutional layer and pooling layer. Note the addition of these dropout layers. These dropout layers essentially are used to help prevent overfitting of my data. So what they essentially will help do is kind of ensure that I don't overfit my data, because in the case of overfitting I may have close to 0 training errors, but my testing error would be significantly higher. Note again, this is a much smaller image data set, therefore we have just about 7 MB worth of weights, which is again fairly significant in terms of pure numbers. This also trained much faster. This trained in about 90 minutes. In about a 90-minute time frame, we had about a 62% accuracy. But let's come to the fun stuff. Let's actually come to some of the results. I mean, this was a lot of data being thrown in your face. Let's talk a little bit about the results that we achieved. What we decided to do was, we decided to take forth images of our professor and our 3 TAs. So here you have David, you have Eric, and you have Sanjana, and you have Professor Lin. We decided to take their faces, and we kind of decided to identify which celebrities that they matched the closest. And these were the results that we obtained. So we had the professor matching Mark Wahlberg, we had Eric matching Matthew Broderick, we had David matching John Cusack, and we had Sanjana matching Lea Michele, which is, again, if you look at it, these are pretty good results considering the kind of accuracy we've achieved. Consider this fact, however, because it's about only a 50% accuracy, you also have a large number of scenarios where you do not have very good matchups. And we had some of our friends volunteer for us, and these were some of the results that we had. We got image mismatches, we had missing hair in some cases, we had absolute gender disparities, we had facial hair being detected, and so on. If you notice, perhaps the common structure in some of these is you had a similar kind of hair being detected here, you had a similar shape and structure of the smile which was perhaps detected. What you notice here is the kind of hair structure here, the shape of the hair is partly similar, and what you notice here is perhaps something like the chin being detected by the algorithm. Again, just a quick pointer, 50% accuracy may seem less, but if you consider multi-class problems such as the CIFAR 100 dataset, which basically has only 100 different classes, that has accuracies of only around 60 to 70%. We are working with a problem which is 5 times more complex, 5.3 times to be more precise. You've got 530 possible classes, and being able to classify them with an accuracy of almost 50% is a pretty good achievement. Let's look at the other set of data. We also spoke about the emotion detection part. The emotion detection part, some of which for similar images, worked out to fairly good results. You see over here, one of our friends volunteering for us looks happy. You see a sense of fear over here. You see this baby's happiness. He was our best model. But you also see a fairly mixed response and debatable responses for something like this, because this was a fairly fear-inclined neutral expression, but this would probably be classified by a human as a neutral expression. Note again that this was an algorithm which was trained over 90 minutes, giving you 62% accuracy. The accuracy could significantly be improved with better qualities of images, and we kind of did run a few tests where we kind of augmented some of the images. We did have some improvements, but that was not a perfect task, and that's why we did not go ahead with that approach. So this kind of broadly classifies our whole project in terms of what we've done. We spoke about facial recognition as a task. We spoke about emotion detection as a task, and we've already spoken about some of the application areas in detail in areas such as biometric security, targeted marketing, in e-learning, in law and order maintenance, in healthcare, and so on. So with that, I'll quickly close this presentation. Thank you so much for watching. Do share any feedback with us in the comments below.